So far, we've been dealing with ideal fluids. However, in the real world, all fluids undergo viscous flow. This is when the layers of motion in the fluid interfere with each other. It is also important to note that viscosity is dependent on the temperature of the environment in which the fluid is in. As the temperature increases, viscosity increases. Likewise, as the temperature decreases, viscosity decreases. When we talk about viscosity, we usually refer to it as viscosity at a given temperature. The unit for viscosity is Pascal seconds. This demo will focus on viscosity and its relationship to the terminal velocity of an object, let's say a spherical ball, dropped through a tube of viscous fluid. The viscous nature of the fluid implies that the ball will experience a drag force acting against it while it is moving. The relationship between the drag force and the ball's velocity is given by Stokes' law, which is presented on screen. N is the viscosity coefficient of the fluid. This is a constant value. Note that the textbook uses a different symbol to represent this variable. R is the radius of the falling object, the ball in this case, which is also a constant. V is the ball's velocity, which is the manipulated variable. The derivation for the equation on screen is in the textbook on pages 579 and 580. The video will not go in depth into the derivation, but the equation is based on Stokes' law combined with the buoyancy force equation, ultimately resulting in the balancing of forces acting on the ball. The important thing about this equation is that the terminal velocity of a ball in the fluid is inversely proportional to the viscosity coefficient of the liquid, as the rest of the variables in the equation are all constants. Each variable is outlined on screen. We just saw a ball being dropped through a tube of oil and then water. Both are viscous liquids and both were of the same volume. Even though the fluids' densities were different, the difference is minimal, and it had significantly less of an impact on terminal velocity than the viscosity of the liquids themselves. The other constants are however applicable to this demonstration. We cleaned the ball between trying both liquids so residue from one liquid would not impact the ball's motion in the other liquid. The ball reached the bottom of the tube filled with water faster than it did in the tube filled with oil. This implies that the terminal velocity of the ball dropped through water was larger than that of the ball dropped through oil. This makes sense because we know that water is less viscous than oil. This demonstration thus confirms the relationship that terminal velocity is inversely proportional to the viscosity of the fluid.